Yeah, thanks everybody for showing up to the first tech talk of the quarter. So we're in the winter quarter here, and this is the third series, and we've chosen to have security be the theme for this quarter. So we've got 5 of these talks set up. They should be on your calendar, but you can always go to the web page. There's a link right from the homepage of ECS that you can see all the talks that are scheduled. We've got the first 3 are going to be from core cybersecurity researchers, and then the last 2 are going to be more cyber physical system security from some of our electric network security researchers. So this first talk is I'm very happy to have Mike Rosulek. He's an associate professor here. Time flies. He came to us from the University of Montana. We were lucky to steal him from them, and he got his PhD from the University of Illinois in Urbana-Champaign. He's really well known for his work in security, various aspects, but a lot of he's got some really nice theoretical work on privacy and computation. The types of things he does just seem like magic tricks to me, and hopefully you'll get some flavor for that, and he might be able to convince you that they're actually real and they can actually work. I know he's been working on making these systems practical as well in recent years. So with that, I will be quiet and let Mike take over.
Okay, thanks, Alan. And just want to echo what Alan said. Thanks, everyone, for taking time out of your day to come see what's going on here at Oregon State, especially in the security realm. So like Alan said, I'm a security researcher here. My area of focus is cryptography. And specifically, I study a problem called secure multi-party computation. And my assumption today is that you may not have heard of that before. So I'm going to give you a very high-level overview of what this actually means. I think my target audience for this talk maybe our friends in industry who are thinking about maybe this is a new tool that they can add to their toolkit to protect some of their sensitive data. It's not going to be a terribly technical talk, so if things seem like magic, I may not be able to lift the veil and demystify what's going on at a technical level. So I hope that's all right with you. So my number one goal for the talk today is just for you to understand what this problem is, because it's a little bit mysterious at first. And the way I'll do that is by showing many examples. I think that's the best way to understand what secure multi-party computation is, what it does, and when it's useful. And maybe give you a little bit of a checklist for when it might be useful for you in your work, if it's a tool that you might think about deploying at some point. And then I'll give you a peek into the research activities that are going on here at Oregon State in my research group, and some outlook about the kinds of things we're working on, and show you some highlights about the things we've done, some bragging about the cool things that we can do. I also want to say that I'm very happy to have comments or questions during the talk or after the talk. I don't mind if you interrupt. I have the chat window open, actually. If you feel like asking a question in the chat, I'll try to answer that, or you can use the raise hand feature. I've become a little bit of a pro on using Zoom lately, so I've got all the channels of information open. Feel free to unmute and just interrupt and ask a question. That's all fine. So I just want this to be kind of a casual discussion between friends. I hope that's how you see it too. Okay, so the premise is that maybe you've seen this expression before, that data is the new oil. It's a valuable asset. Companies using data to power all their analytics and personalization. Machine learning has caused many organizations to be really hungry for gathering lots and lots of data. But on the other side, it's toxic, just like oil is, because the main thing is that holding lots of sensitive data leaves you open to liabilities, makes you a target for attacks, those sort of things. You have privacy regulations that you have to deal with. So you have to be careful about data. And so secure computation is one of these privacy preserving tools that's relevant for sensitive data, private data. And the way I like to think about it is that it's like a centralized computation, but decentralized at the same time. So what do I mean by that? So imagine that there are different organizations that each have sensitive data, private data. That's the decentralized aspect. There's data that's sensitive. It's distributed among different participants. But it would be beneficial if that data could be brought together centrally and computations performed on it. I'll give you many, many examples throughout the course of the talk of kinds of sensitive data and the kinds of computations you might want to compute on them. But just imagine if it, what we would really love is to just put all the data in one place and then run some analytics, some computations on that data. But the fact that the data is privacy sensitive means that we can't actually put all the data in one place. Maybe the participants don't trust each other. Maybe there are privacy regulations. Maybe it's just bad business decision in terms of liability and so forth. So that's the premise. Secure multi-party computation is a way to achieve the same effect of centralizing the data for a computation, but done virtually through an interactive cryptographic protocol. So instead of shipping everyone's data to a centralized location, the participants just run some cryptographic protocol. It's interactive, so they send many messages back and forth. They're using fancy cryptography that allows them to run a computation on the data while it's still hidden. You can think of it as performing a computation in the encrypted domain rather than in a plain text domain. So this is the things that I study are cryptographic protocols. They take in private input from the participants. Before this interaction starts, all the participants agree that we want to compute this specific function of the private inputs. Maybe it's some sort of analytics, maybe it's a machine learning classifier, maybe it's machine learning training, but we agree we're going to we have this data, we're not going to share it with each other explicitly, but we want to run this specific computation on the data, and we want to learn only the output of that computation. All of the intermediate steps of the computation remain hidden, and in particular, all the inputs to the computation remain hidden. I think that's what I said there. And this is something that we can do while providing kind of the best cryptographic security guarantees, the kinds of guarantees that you're used to from things like encryption, things like HTTPS. Those come with the best possible guarantees that the cryptographic research community knows how to provide. And we provide, analogous guarantees here about the kind of information that's leaked through this process. So some information about the input data is leaked. Specifically, the output of these pre-approved computations is leaked, but nothing else is leaked. And that's what we can guarantee in a provable way. So it's not like the things that we do in this field are not like heuristics about adding noise to data to sort of obscure it. That's a viable approach, but in some cases it can just be a heuristic. So here we're not interested in heuristics. We're interested in kind of full-fledged cryptographic security proofs. Okay, so as I said, most of this talk is just me trying to paint the right mental picture in your head through means of several examples. Some of the examples are hypothetical, just problems that I've noticed out in the world, not just me, but problems that are out in the world that maybe secure computation would be a good fit for. Some of the examples are real world applications where people are actually using secure computation to solve these problems. And I'll try to indicate when one of these examples is hypothetical and when it's kind of a real world example. So in this first example is a hypothetical one, just to sort of paint the picture. This is like a classic analytics over federated data kind of situation. So imagine that Portland wants to plan its transportation infrastructure for the next decade. If you're planning transportation infrastructure, you need to understand, the current situation with people moving around through Portland. Where does that data live? Well, some of the data, in 2021, some of that data lives, for ride sharing services like Uber. Some of it lives in bicycle sharing services. Some of it lives in public transit services. So a lot of different data about the movement of people through the city, held by different organizations and companies. Wouldn't it be great if all these organizations just opened up their databases to the city of Portland, and the Portland could just like run all the queries that they want on these combined databases? Well, that's not going to happen. That's not going to happen. But what they could do is these organizations could get together and agree to run some sort of joint analytics on the union of all their data, and the analytics have been chosen by the city of Portland, and everyone agrees that they're willing to release this, the result of these analytics. You might be surprised to learn I'm not a transportation engineer, so I don't know what kind of analytics they would be interested in, but this is a kind of a classic example. So before I move on to more examples, I also want to give you my little checklist about when secure computation is a good fit. I really like working on secure computation, but there's a risk that I might think that secure computation solves everybody's problems everywhere. And that's not true. And I don't want to paint that picture. I want to give you a realistic picture of when to use secure computation, especially informed by the state of the art and what is actually practical and feasible today. So secure computation, the current techniques that we have, they work best when there's a small number of participants, like 2 or 3. So you see that frequently in the examples that I'm giving here. In the previous example, it was City of Portland and a small number of organizations like Uber and public transportation. Secure computation works best when the identities of the participants are known and kind of fixed, right? So City of Portland knows that it's going to participate with Uber. It's not a situation where some anonymous person comes along and wants to participate in this computation, right? It's well-known identities of the participants. It's usually 2 business organizations, 2 or 3 business organizations. The fact that a business is doing this interaction means that sometimes there's a disincentive for certain kinds of cheating. So if you know that there's a financial or a reputational disincentive for cheating, then the cryptography can be a little bit simpler. If you know that there's externalities that mean that the person is not likely to cheat in these crazy ways, then we can assume they don't cheat in these crazy ways, and the cryptography can be a little bit simpler. As I said, secure computation is an interactive protocol, so the participants have to be online at the same time, generally speaking, and they have to kind of interact synchronously. So if it's a situation where maybe I can only send out data but I can't receive it, or I can only send something and then I go offline because I'm out of signal range, then that might not be a good fit for secure computation. So all of these are like long-term fixed identities, a good possibility for interaction. That's my checklist for who's participating in this process that would make it suitable for secure computation. Now, in terms of what computation the participants want to do on the data, a good rule of thumb is that if you can do something fast in hardware, then it's a good fit for secure computation protocols, because actually the way they work is similar to compiling the computation down to the hardware level and then executing things at the hardware level. It's kind of, it's maybe a bit of an analogy, but it's a pretty good analogy to how these protocols actually compute on the data without really looking at the data. It's best if the inputs to the computation are structured and predictable. Doing things like sanitizing data or dealing with noisy, fuzzy, non-normalized data, that's really hard. It becomes expensive to do that inside of this crypto protocol. It's better if all that can be done beforehand, and then you provide really nice, clean data to the secure computation. Also, there's no, you don't necessarily get feedback, right? We agree to run this computation and learn only the output. Well, then if you have some sort of mistakes or inaccuracies in your data, all you get is maybe a strange output that you don't understand. There's no feedback. Like in a normal computation, you would get some feedback you can maybe debug. Here, you sort of give it all up to the crypto gods and you get the output at the end. So that's good. Simpler computations really work the best. So secure computation is for situations where the barrier to actually doing this is this centralization issue. The privacy sensitive nature of the data prevents you from centralizing it to compute on it all at once. It's not that you're trying to compute something that's really complicated, because actually if you put this crypto stuff on top of it, it's even more complicated. So it has to be the privacy and not the sophistication of the computation that's the barrier. And last, we're adding some extra crypto stuff to these computations. It adds an overhead, it adds latency. So this is maybe not suitable for real-time computations. You don't want to use secure computation to like blindly evaluate a neural net on your car to determine whether something is a stop sign, right? So things, business reports where you just need something, to run over the weekend and have the report finished by Monday. Those kind of things are a great fit for secure computation. And we'll see that some things can be very fast. I usually measure fast on the order of seconds as opposed to minutes and hours, but maybe not milliseconds, let's say. Okay, so I'm going to continue to move on to more examples, and we'll kind of look back at that checklist and see how these examples reflect those things that I listed on the checklist. So here's a real world example, maybe one of my favorites. So I guess in 2016, the city of Boston said, we want to know whether the tech companies in Boston are paying women and men equitable salaries. Right? I think the mayor of Boston said, I want to know the answer to this question. Go figure it out. And it was kind of a perfect storm because at Boston University, there's a really strong group of people working on this secure multi-party computation problem. So what they did was they recruited 250 companies to submit encrypted versions of their payroll data to 3 different brokers. So they encrypted the data and sort of distributed among 3 main brokers. So there's Boston University, this Workforce Council, and City of Boston, like the local city government. And then those 3 organizations did a secure computation to do various queries on the data. So if you think about this question about whether tech companies are achieving pay equity, if you have the data, that's a reasonably easy question to answer, right? You compute some medians, you compute some averages, you group different records into different bins based on gender, age, seniority, and you compute these simple statistics on those categories. So it's not as if the city of Boston wanted to run really complicated statistics. It was like things that if you had everything in a spreadsheet, you would be able to do, in an afternoon. So it was really a problem of getting tech companies to share this data. But now the input data was distributed. It was certainly privacy sensitive. And somehow because they had the backing of the city and they had this mandate from the city, they're able to get 250 tech companies to actually sign up to use this crypto wizardry to answer this question. It's pretty amazing to me that they were able to do this. But they did this. They've been doing it ever since. So they first used this technique in 2017, and they've been using it ever since, as far as I know. The last time I checked, they're certainly still using this secure computation technique. So that's my absolute favorite example, I think. Yeah, the things that impress me are all these, non-technical things about how you actually get people to use these crypto tools that I'm working on. Okay, here's another real-world example. This is an example that got some kind of negative press, maybe rightly so, but this is one of the things that explains Google's interest in this technology. So Google is an advertising company. They have a list of all the people who have seen any given advertisement. And MasterCard has a list of all the money that people spent around the world. If you could combine those two data sets together, you could understand how effective different advertising campaigns were, right? You would say, show me all the people who, find all the people who saw this ad, and then look at how much those people spent at this store, and give me some statistics about that. Again, those statistics are very simple. If you had all this data in a single database, you could write it in a very short SQL query. The data is highly structured. The data lives at two places, so there's only two fixed participants, and they're Google and MasterCard. You know exactly who they are. They have good network availability. So this was a pretty perfect fit for secure computation. So Google is known to use this technique to kind of get feedback on how effective their advertisement strategies are for their advertising customers. Okay, here is another example. Let me just make sure I'm doing okay for time. This is an example that I just wanted to give because it's a pretty hot topic right now. So in this scenario, you have a company like Itron who manufactures power meters, and they have expertise in modeling power systems and power usage and that sort of thing. Utility company like PG&E has all the data from everyone's smart meters. It would be great if they could pool their efforts to help PG&E understand power usage, so they can, tweak their distribution networks. Notice when some blackouts are coming or some power outages are likely. So what would be great is if you could take the meter data that the electric company is seeing and use a machine learning classifier that's been trained by someone like Itron who has expertise in the modeling thing. This is a classic example of machine learning classification on private data, right? So one participant has a classifier that's kind of their proprietary product, and another participant has the data that they would like classified, but it's private, privacy sensitive data. So you can't put them together, but you can put them together virtually in a secure computation protocol. Yeah, classification as a service, very hot topic these days in my research area. Wow, I have so many examples. This is fun. I hope you're starting to get a sense of what kinds of problems this technique can solve. So this is a real world example. If you're using the Chrome web browser, it has a built-in password manager. So the browser knows all of your passwords. Okay, that's a good thing. They're all encrypted. It's safe. It's fine. But it's not fine if you're using a password that has been breached. Right? Every year, many companies get broken into, and millions of users' accounts are compromised. Their passwords are leaked and sold on the black market, or it's dumped on a website somewhere. And bad guys use those lists of breached passwords to try to break into your other accounts. So you don't want to use a password that has appeared in one of these breaches. You also want like a notification, kind of like a credit report. It'd be great if someone could just tell me that, hey, Mike, one of your accounts was breached. The login and password has been found on some website somewhere. You need to change that password right now. So that's exactly what this password checkup service does. Like this is an official Google product, and I think at the time I took the screenshot, it was an extension to the Chrome browser, but now I believe it's built in. So what's the computation we want to do? We want to take all my passwords, and we want to take the list of all the passwords that Google sweeps up from the internet that have been found in various breaches, and we just want to see if there's any overlap. We want to see if there's any items in common between those two lists. An extremely simple computation, right? It's just the intersection of two lists. But of course, I'm not going to give all of my passwords to Google in the clear, right? They're in my password manager, but they stay encrypted on my, and only I can decrypt them. So this feature of the Chrome browser uses secure multi-party computation to compute this intersection. So you only learn which of your passwords are showing up in breaches across the web, and in the process, Google doesn't learn anything about your passwords. It's a really, really great privacy tool for regular users, right? In contrast to the other thing that Google does, which is tracking all of your purchases with MasterCard. This is like really users first. So I like this one a lot. I think that was the last main example. So this secure multi-party computation thing sounds really magical and amazing. And what's really amazing is that the crypto community, the research community, has known how to do this in theory since the 80s. It's kind of shocking. So this idea came up in the 80s, and it was shown that in principle you can securely compute any function of private inputs, like anything you can compute. In principle, you could do it with this within this multi-party computation framework. But it was clear that this was going to be so slow and inefficient that no one really took it seriously as a practical idea. I mean, it was taken seriously as a theoretical idea, and in the 80s and 90s, lots of work was done on the theory, and then maybe in the mid 2000s, people started to implement it and thought, well, maybe if we work on this, then we can get this to be practical and efficient. And since I've been working in the field, maybe over the last dozen years or so, we've seen it become much more efficient. So here's a chart that I stole from one of my colleagues, and it's really only showing the last, since 2009. So it's showing the last 12 years or so. And this is like some benchmark computation that you can measure how long it takes to do inside of a secure multi-party protocol. And things have gotten like 1,000 times faster over the last just 10 or 12 years. So a little bit of that is due to improvements to technology and hardware, but most of that is due to fundamental algorithmic improvements. So I think in the 2010s, we're starting to see a few adoptions of this in real world applications, like some of the ones that I showed you. I think in the next decade, we're planning to see lots of adoption. People are starting to know about secure multi-party computation in places that we wouldn't have expected 10 years ago. So it's been a really good success story in terms of improving the efficiency of these kind of tricks. So now is the part of the talk where I give you a little bit of a showcase about what's going on here at Oregon State within my research group. So we are focused on mostly the theory side, but the theory side kind of informed by what's needed for practice. So I like working on fundamental improvements to these protocols. So I like designing new protocols, but we also build lots of prototypes and proofs of concept. This is kind of the core thing that we do in my group. Yeah, this seems too self-serving. I must move on from this slide. So here's one of the things that we've done a lot of work on over the last few years. So a special case of computing on private data that's called private set intersection. So actually, if you recall the example that I gave about this password checkup feature, we want to find out which of my passwords also appear in a list of passwords that were found in breaches that were posted online. That question is just the intersection of two sets of items. We want to find which items we have in common. So that's private set intersection. Two parties, each of them hold a set of items. They want to know which items they have in common. I think I have one more example of this in the next slide, actually. But this is something we've done a lot of work on. I guess my research group is kind of the leaders in this particular problem. And this is something that's surprisingly efficient. Maybe I have a weird perspective here, but I find this to be very, very efficient. So what we can do in terms of intersection is if each participant has 1 million items, they want to compute the intersection. It takes less than 4 seconds and maybe 100 megabytes of communication, which is non-trivial. It's not free, that's for sure. But I'm really proud of the fact that it's only 5 times slower than doing the computation without any security at all. And when you look back to maybe even 5-10 years ago, anything you did was like 10 million times slower than doing the computation without any security at all. So that's one of our proud achievements here. Here's a specific example of private set intersection that I really like. So when you download WhatsApp onto your phone, you need to know which of your friends are on WhatsApp so you can send them messages on WhatsApp, right? So what happens is you download the WhatsApp app. The first thing it does is says, hey, give me access to all of your contacts. And then it sends all of your contacts up to the server in the cloud, which is owned by Facebook, by the way, because Facebook owns WhatsApp. And Facebook says, oh, here are the friends that are in your address book, which are also users of WhatsApp. And now it populates your list of contacts on WhatsApp, and now you can send them messages. The computation that's going on here is just an intersection. We want to find the intersection of my address book on my phone and the list of all users of WhatsApp. This is called contact discovery, but we want to make this private because some of us don't want to send our entire address books off to Facebook, for example. Your address book contains lots of bizarre people that say something about you, right? So this is a case of intersection of sets where I have a small set, maybe 1,000, less than 1,000 people in my contact list, but there's a billion users of WhatsApp. So we had to design special protocols to handle this asymmetry in the size of the input sets. So the intersection of a huge set with a small set. And we built a prototype that's, I'm giving you the numbers here on the screen, where the big set was 250 million items, the small set was 1,000 items, and we could compute that intersection in 5 seconds and only 5 megabytes of communication. We wanted to make the communication small, thinking that this is something that you could run on a phone. So, we're very happy with the performance. It's not fast enough to be deployed if you have a billion WhatsApp users, and then they all periodically, do some maintenance to check whether any of their contacts have recently, joined WhatsApp. So it's not quite fast enough for that, but it's getting quite close. So that was a prototype that we built, and we were pleased with how it performed. Here's another prototype that we've kind of been working on in progress. And we found this organization that's based in Salem, actually, and their job is to find people who are double registered to vote in 2 states, or other kinds of maintenance on the voter registration system. So actually, there's a consortium of states that all send their voter registration info to the centralized location, and then this organization tries to find, it generates a report for each state saying, this person looks like they're also registered in a different state. You might want to look into this, those sort of things. So we thought, well, maybe it would be nice to do this with secure computation, so we don't have all of the voter registration information in the country, sent to a single location. Maybe we want to avoid that, a central point of failure. One of the tricky things is that voter registration doesn't use your social security number. So there's no universal identifier for voters in different states. So I can't just say, give me all the social security numbers registered to vote in Oregon and all the social security numbers in Colorado, and we'll take an intersection. Your Oregon voter registration is based on your your driver's license number. And then the DMV has the mapping from your driver's license number to your social security number. So we developed a system that within each state, it would map your social security number to your voter registration number. And then across the states, it would try to find, people who are double registered to vote. And we ran this with kind of medium-sized, with data sets that sort of reflect medium to large size states, like 16 million voters. And this is something that took a few minutes, less than half of an hour. Lots of data transfer, but less than half an hour. And for something like this, it's not a real-time, these are not real-time reports that you need to generate. You maybe generate a report. You could certainly generate a report once a day, and that would be fine for this kind of application. So that's something that we've worked on as well that we're proud of. Okay, so I'm wrapping up a little bit, and I see I have some questions in my chat, some direct messages. I'll answer those as well. So, but I'm wrapping up here. So we have this cool cryptographic magic, I guess, according to Alan, that's been around as a theoretical curiosity since the 1980s, and slowly building some momentum. And now it's starting to be deployed, and I think we're going to see it's practical enough that we're going to see it used for lots more things. The current research challenges that we're working on right now, I've listed here. So composition, if you look back at this previous example where within each state we wanted to link, sort of link social security numbers and driver's license numbers, but we didn't want to reveal that information in the clear. We wanted to feed that into another secure computation to find the intersection between states. So this idea of composing these different building blocks together is a major challenge, because security is kind of fragile. And just because one part is secure and another part is secure, if you put them together in the wrong way, you might lose all your security. If we want to see this stuff actually deployed, we need to work on integrating this into real world data sources, data flows. That's a major problem. Scalability is always a natural research problem. If we really want to protect the privacy of people who sign up for WhatsApp, we need things that scale to billions of items. And we're doing pretty well for scalability, but we're not quite ready to have a drop-in replacement for the contact discovery of WhatsApp, for instance. It's also a major challenge to scale to many, many participants, right? So all the examples that I gave have a very small, usually 2 or 3 number of participants. And finally, the hot topic these days is optimizing all these techniques for machine learning types of applications. So all the interesting computations that people want to do on private data seem to be from the machine learning field. So can you optimize these techniques? Right, we have optimized techniques for things like intersection of sets. Can we have optimized techniques for training a neural network classifier, right? How do you do some back propagation machine learning algorithms on private data, those kind of things. So that's the end of my talk. So I'll be happy to take questions. I appreciate your time and attention. I have some questions in my chat. Some of them are private. I can just go ahead and start with those. Does that make sense, Alan?
Yeah. Perhaps we could just have people, also just speak up, raise your hand, and if you've asked a question in chat, it's always nice just to ask it out loud. So we could start with that, perhaps.
Sure. Yeah, anyone who asked a question in chat is welcome to bravely unmute their microphone.
Yeah, I see Charlie, you asked a question in chat. You wanna start off?
Oh, sure. Actually, I have 3 questions now that I look at it. One is the encrypted data quantum computing resistant, so that it could be used for very highly sensitive applications that have long-term data in it? Another question is, how much setup is required? Do the multi-parties have to have keys distributed, or how is the setup performed such that 2 parties can share the data? The last one I was curious about is, has there been analysis done on this in terms of side channel attacks on the CPUs themselves?
These are great questions, and I'll try to remember them all. Thankfully, you've got them written down in the chat. So quantum computer resistant, so some parts of crypto are affected by quantum attacks and some are not. And that's also true of this setting as well. If there are a couple fundamental building blocks that we use in these protocols, and for the most part, if those building blocks are resistant to quantum computers, then the whole protocol inherits that as well. I would say that all of our prototype implementations generally are using kind of the building blocks of today, which are not, they're vulnerable to quantum attacks, just because those are faster today. But in principle, you can always swap out these components for quantum resistant ones, and the entire protocol would inherit that property as well. Your next question was about setup. There's no need for setup. Basically, you just need a secure channel to talk to the other participants. So it's maybe convenient if people have certificates. You just need to authenticate that you're running this protocol with the right person, but there's no need for, so there's no absolute need for a setup beforehand. If there is a possibility for a setup beforehand, like certain shared keys, that can improve things, but it's not absolutely necessary. Things can be done without it. And then your last question has slipped my mind.
Side channel attacks on CPUs.
Side channel attacks. I would say probably not in this realm. My cynical answer is that, wow, if people are asking about side channel attacks, that means we're doing really well as a field. Because people are actually worried about running this in the real world. So it'll be a fantastic day when someone attacks a system attacks a secure multi-party computation protocol using a side channel attack. That would be a great day for us, because that will mean that we're relevant. But I would say we have enough challenges without getting to that point. Although I will say that you're computing on private data, so if there was an obvious side channel attack, it would already undermine the security property that you're going for, right? Because you're supposed to be computing on things without knowing what you're computing on. So in some sense, there's already kind of a natural resistance to side channels. But yeah, but maybe, there's always a possibility for other side channels though, but like fundamental side channels might already just not matter just because of the nature of the security guarantee. Like really, we prove that nobody can see the data. So it's hard to have a side channel that leaks information about that kind of data.
Yeah, hey Mike, this is Rakesh. That was my clarification on Charlie's question, is what kind of side channels did he mean? Did he mean hardware side channels, or is he talking about, there are other crypto side channels, right, that you probably already the proof deals with. If it's a hardware side channels, then that's, I think what you're saying makes sense. Yeah.
Yeah, I think the mathematical protocol can't really leak anything about the private data, but side channels could leak something about the crypto stuff. And then then that means the crypto building blocks are leaking and unsound, and then you might inadvertently leak some information about the private data.
Yeah, so Tom, you've got your hand raised.
Yeah, my only question was, I was surprised at the huge communication cost of your last example.
Yeah.
What drives that?
That's a good question. I'll have to recall what we actually do in this paper. I would say that, boy, that's a hard question to answer. If you compare it to something like this, which had super small communication.
Right.
In this problem, I have all of my data in the clear, and WhatsApp has all of its data in the clear, and we're just checking to see whether two things are equal. And that's something that we've optimized to death, and we have tricks for that. In this situation, we were considering that even within the state of Oregon, the DMV and the Secretary of State voter registrations didn't want to share their data in the clear. So they kind of reconciled their data in the clear, mapping voter registrations to social security numbers, but neither of them had those records in the clear. So even the participants have data, intermediate data that they don't hold in the clear, and then they have to make comparisons on that data in the clear, and that's much more expensive.
So this really is an example of your composition. You have pairs of pairs.
Yeah. So this was a prototype for a project where we are trying to do composable set operations, like unions and joins and intersections and database-like operations in a composable way. And this was our killer application for that paper.
So Prasad had a question. I'll just read it. So why is it hard to generalize to more parties? And I might add to that, the Boston example had 250 parties on one side and 3 brokers in some sense.
Yes.
So it seemed like they must have been doing something fancy or, yeah.
Yeah. I have a lot of lag here on my office thing. Okay, so to generalize to multiple parties, there are some techniques that really, so somehow two versus 3 is kind of the main question. So there are some techniques that really only work for 2. It's maybe hard to articulate why that is, but yeah, there are some techniques that just work for 2 and they don't work for 3. Most of the things that work for 3 work for any number of parties, but they just scale poorly, right? They may scale quadratically in the number of parties because maybe everyone has to talk to everyone else. So it's not like a theoretical problem of how to do that, but it just doesn't scale very well. In this particular example, there's only 3 parties actually doing the secure computation protocol, and that's the university, this workforce council, and the city government. There were 250 companies that submitted data, but they just submitted and then they went offline. So only these 3 participants were actually doing the crypto protocol. So what the tech companies that provided the data sort of split their data between these 3 participants. It's like if I give Alan a key and I give Tom my encrypted data, but he doesn't have the key, then neither of them know any information individually, but they can, inside of the crypto protocol, they can virtually decrypt it and then do some processing on it. So that's what happened here. So this was not a secure computation among 250 participants, but among 3.
Okay.
So they were clever to do that.
Yeah. And so we have another question. Can you say more about the classification as a service that you mentioned as an expanding field? So I guess what are the so where are we there now? Where are we now? You can maybe run a classifier. Are we even close to training a classifier? Or?
I've seen a few papers training classifiers, but simple ones. Definitely not neural net training. Okay, so for classification, there's a lot of papers. It seems like in the last 2 years, every paper on this topic is with applications to machine learning, privacy preserving machine learning. There's workshops on privacy preserving machine learning. Usually that's just classification. So classificate, there are some decision tree classifiers. Those are really, really simple. Those can be done efficiently. Neural networks are a little slower. I'm trying to think here. I've seen some classification. Classification is tough because it's a really iterative process, at least for neural network training, very iterative. And all these iterations lead to round trips in interaction. It ends up being very, very, very slow just because of the number of round trips. But I've seen some work on training simple classifiers like decision trees. So I'm not an AI person and I'm going to demonstrate it, but things like support vector machine kind of things. But training neural networks is not really practical at this point.
Okay, yeah, thanks. So I actually have to jump off to an actual telephone call, but I will actually leave you on. I don't know how much time you have, and anybody else who wants to talk to Mike can feel free to stick around. And so I'll sign off, but I hope to see you all in 2 weeks when we'll have our next speaker. Thanks for attending.
Yeah, that sounds good. Thanks, Alan. And I'm not going anywhere. I do not have a meeting at 12. So.
Right, you're the new host.
Okay, wow. with great power comes great responsibility. Let's see.
So, hi, Mike. This is John Brewster.
Hi, John.
At HP, we did a lot of image processing, and very similar problem shows up in when you compress the images, and then you want to do processing on them. You don't want to decompress them, do your processing, and recompress because it's all very lossy. And so I'm just wondering, is there a close cousin here where we're operating in a very different data domain where we have to develop new approaches of interacting with that data without ever actually decompressing that data?
Yeah, I think that's a good analogy. I don't know if the techniques would be analogous,
right?
But certainly the high level idea is a good analogy. I think I think our demands for security are pretty strict, and the data has to be kind of encrypted in a very special way if you're doing certain operations on it blindly.
Yeah, I mean, more on point, we were very interested in the machine learning attributes of this problem, where not the image processing, but just the general case that you were walking through, where we wanted to know things like, is a machine going to fail in the next 2 weeks? And doing the machine learning of a neural net that would do that on the private data across all the users of those machines. Very, very active problem for us.
Yeah, it's a lot harder when it's like end users that are being involved in this crypto protocol, because then you worry about them just kind of not following the rules, and you don't know who they are beforehand.
Well, the other problem is for industrial customers, right? Because they're the ones spending millions of dollars on hardware that really needs to benefit from this, and you know, they care about their privacy of their data in really extreme ways, you know, contractual ways.
Yeah, they don't mess around.
Right. Thanks.
I see a question in the chat from Aliyah that I wanted to address. So the question was some of these protocols names to look up for more information. We don't give the protocols names too often. It's usually just named after the authors of the paper, and there are hundreds of those. But I'm going to do a shameless plug. Just a second. So there's this book which you can find online. I'm one of the authors, and it's just an introduction. So if you want to learn more about the actual techniques, this is a book.
Can you hold it up one more time? I'll get a snippet.
Yeah, I don't remember. You can find it for free online. I don't remember our website, securecomputation.org, multipartycomputation.org, something like that. It's kind of a survey that we wrote and published last year, 2 years ago, and it's an introduction to the protocol techniques. It's not heavy on actual security proofs and stuff, but it gives you an idea of how these techniques work. That would be a good starting point. And I appreciate the opportunity for another shameless plug. Thank you for that.
Mike, you have a question from Mark.
Okay.
I can read it off. When do you think smaller groups can become active in this space? The organizations you mentioned are often large and resourceful. Thank you for the presentation. So
that's a good question. I don't think you need to be, a $1 trillion tech company to actually implement this stuff. You just need to be willing to be kind of an early adopter at this point. And you need to convince your legal team that you can put, if there's data that's kind of sensitive, you need to convince your legal team that it's okay to put this sensitive data into some, cutting edge crypto stuff. I've always thought that secure computation can be a way to deal with privacy regulations like GDPR or other like certifications, like security certifications. Because from my perspective, we're offering the same security that you would get from just like, you're supposed to encrypt the data at rest, and we're offering, analogous guarantees. But I'm not a lawyer, and I know that you need to get the lawyers on board with that kind of stuff.
So you're saying there are no computational or storage cost barriers for small organizations to get into this, right? I mean, that's what you're alluding to, right?
Right. So yeah, it's you don't need a supercomputing cluster to do this stuff, and all of the numbers that I reported are, they're usually run on my grad students' laptops. When I give these numbers that such and such thing cost a couple seconds, it's either on my grad students' laptops or on middle of the road Amazon cloud servers. So there's no huge investment that's needed. You just need to have a cryptographer in your corner, I guess. Find one of us who's studying it in the field, or find one of our grad students. But I admit that I'm not really a business person, so I don't. I can say that there's not really technological barriers. Maybe barriers in terms of integrating it with your existing data sources, but for some problems, it's definitely ready. It's not polished. It's not an off-the-shelf thing that anyone is prepared, but the technology is there. That's at least my perspective.
Oh, Charlie has another question, but before we go to Charlie's question, I wanted to add. So the technology is not polished, you say, but aren't there libraries that are developed so that people could implement these schemes now? There are open libraries to implement these secure multi-party computation now, right?
Yeah, there are libraries, and I would classify them in a range from research prototype to aspiring production ready library. I don't know if there's a clear-cut production library. One that comes to mind is that Google released, they open sourced the tools that they used for this collaboration. No, not the Chrome plugin, but the thing they did with MasterCard. So finding the common records and then computing aggregate statistics. So they made a big fuss about that when they open sourced it. I assume that's reasonably polished because I think it really is it's a good representation of what they actually use to run this.
This also maybe answers Charlie's question: are these side channel ready? So I guess these will be side channel ready when the libraries used to build these protocols are side channel ready, in the sense they're implemented in a way that they can resist side channel attacks, right? Charlie, sorry, I'm passing the question.
Go ahead.
Floor to you for a question. Yeah.
Great. Hey, Mike. So I'm just curious if you've looked at applications in the Department of Defense that has a tremendous number of requirements to information share with our coalition partners. That's, we don't really do operations anymore by ourselves. So, for example, in Pacific Command right now, I think there's 12 different information sharing networks between the US and Japan, and the US and Korea, and then the US and Japan and Korea. And it's crazy. And I'm just wondering if you've targeted any of the research items in that community.
I haven't had much luck with the Department of Defense funding. I was funded by one project that got canceled after about a year. And they were the goal of that project was to build kind of a top to bottom system for developers to develop applications that use this seamlessly. So you would write a program, and then you would annotate. You would say, well, this piece of data actually comes from this person, and this piece of data comes from that person, and then the compiler would figure out how to do the crypto protocols in the background and figure out what are the correct protocols to use. And so on. But we didn't get very far because the program was canceled. And we were kind of isolated from any specific, defense applications that they had in mind. I know there's, is there anyone from Galwa on the line here today? So Galwa in Portland is among other things, they do crypto research, and they do a lot of Department of Defense contracting. And I know that they do use some of this stuff for their Department of Defense contracts, but I don't know the details.
Is that something you'd be interested in exploring?
Yeah, possibly. If any of this kind of strikes you as a good idea, then yeah, be happy to discuss.
Okay.
And just in case anyone didn't see it, I did find the link, securecomputation.org, which I put in the chat if you want to get the free copy of our book and demystify the crypto magic. All right. Thanks everyone for sticking around late. I appreciate all the questions and comments. It looks like the comments and questions have died down, and we're 8 minutes late and people are drifting off. So maybe a good place to stop. So thanks again. Rakesh, do you know who's speaking in 2 weeks? Is that you or is that Youngjin?
I think it's Youngjin next, and then then I'll be talking. So thanks for the talk, Mike. Always a pleasure, and thanks everyone for staying around.
Yeah, thanks everyone. Hope to see you in 2 weeks then.